Hello and welcome to Math Zone African Motives. Today, we're diving into a crucial topic in engineering science N4, dynamics. Our goal in this tutorial is to tackle question 3 from a past exam paper. We'll work through each part step by step to build your understanding. By the end of this video, you will be able to state Newton's first law, calculate deceleration and force using kinematic equations, solve problems involving acceleration and work done, and apply the principles of energy conservation to find potential energy, kinetic energy, and velocity. Let's get started with the first question. Question 3.1 asks us to state Newton's first law of motion. Take a moment to think about what that law tells us. This law, also known as the law of inertia, describes how objects behave when there are no external forces acting on them. It states that an object will keep its position of rest or its uniform motion in a straight line unless acted upon by an external force. This means if an object is not moving, it won't start moving on its own. And if it is moving at a constant speed in a straight line, it will continue to do so forever, unless something pushes or pulls on it to change its motion. So, we have successfully stated Newton's first law, fulfilling our objective for this part of the question. Now let's move on to question 3.2. This problem involves a car decelerating. The question says, a Hyundai i30 car with a mass of 1,200 kilograms is moving along a flat, even road at a speed of 80 kilometers per hour. The brakes are applied, and the car is brought to a halt inside 50 meters. We need to calculate the deceleration and the braking force. First things first, let's identify what we're given. We have the mass, ms equals 1,200 kilograms. We're given an initial speed of 80 kilometers per hour. Since our other units are in meters and seconds, we must convert this. The conversion is 1 meter per second equals 3.6 kilometers per hour. So we divide 80 by 3.6 to get 22.222 meters per second. We are also told the car comes to a halt, which means its final velocity, v, is 0 meters per second. And the distance traveled during braking, s, is 50 meters. We'll tackle part 3.21 next. Let's calculate the deceleration. To do this, we need a kinematic formula that relates initial velocity, u, final velocity, v, displacement, s, and acceleration, a. Looking at our formula sheet, the perfect fit is v squared equals u squared plus 2a. Our goal is to find a. So we rearrange the formula to make a the subject. We subtract u squared from both sides and then divide by 2's. This gives us a equals v squared minus u squared, all divided by 2's. Now we substitute our values into the rearranged formula. We have a equals, in the numerator, 0 squared minus 22.222 squared, and in the denominator 2 times 50. This simplifies to negative 493.818 divided by 100. The result is negative 4.938 meters per second squared. The negative sign is crucial here. It indicates that the car is decelerating or slowing down, which makes perfect sense for braking. The magnitude of the deceleration is 4.938 meters per second squared. Comparing our answer to the marking guideline, which shows a value of negative 4.938 as by ms2, our calculation is correct. We've successfully calculated the deceleration. Next, let's find the braking force. To find a force when we know the mass and acceleration, we use the most famous law in dynamics, Newton's second law. Newton's second law states that the force acting on an object is equal to its mass multiplied by its acceleration. This simple yet powerful formula is F equals ma. We just calculated the acceleration, and we were given the mass. We'll use the magnitude of the acceleration since force is also a magnitude in this context. So, we substitute 1,200 kilograms for mass and 4.938 meters per second squared for acceleration. Multiplying these values, we get 5925.6 newtons. The unit of force, of course, is newtons. The question is worth 2 marks. We've shown the correct formula and the correct substitution. Let's compare our answer to the marking guideline. The memo provides 55925.807 newtons, which it then rounds to 5.926 kilonewtons. The slight difference is due to the memo using a more precise value for the acceleration before rounding. Our answer of 5925.6 newtons is perfectly valid. And we can also express it as 5.926 kilonewtons by dividing by 1,000. So, this part of the question is complete. Let's move on to question 3.3. This problem is about a train accelerating. The question states, a Gautrain with a mass of 195 megagrams is attached to a locomotive with a drawbar. The train uniformly accelerated from rest on a horizontal track. The resistance to motion is 8 newtons per megagram of the mass of the train. The force in the drawbar is 45 kilonewtons. We need to calculate the acceleration of the train and the work done over a distance of 3 kilometers. Again, let's list our givens. We have the mass of the train, m, which is 195 megagrams. A megagram is 1,000 kilograms, so that's 195,000 kilograms. The train starts from rest, so its initial velocity, u, is 0. The resistance to motion, r, is 8 newtons for every megagram of mass. So we multiply 8 newtons by 195 megagrams to get 1560 newtons. Finally, the pulling force from the drawbar F is 45 kilonewtons, which is 45,000 newtons. Let's tackle part 3.3.1, the acceleration. To find the acceleration, we need to consider all the forces acting on the train and apply Newton's second law. The drawbar pulls the train forward, and the resistance acts against its motion. The net force, F net, is the forward force from the drawbar F minus the resistive force, R. So F net equals F minus R. Setting this equal to ma gives us our equation. F minus R equals ma. We want to find the acceleration a, so we rearrange the formula to isolate a. This gives us a equals F minus R, all divided by m. Now we substitute the values we identified. We have a equals 45,000 newtons minus 1560 newtons, divided by 195,000 kilograms. This gives us 43,440 divided by 195,000. The acceleration is 0.2276 meters per second squared. Rounding to 3 decimal places, this is 0.223 meters per second squared. Let's compare this with the marking guideline. The memo also gets 0.2223 ms2, so our answer is correct. We have successfully found the acceleration of the train. Now for part 3.3.2, we need to calculate the work done by the drawbar over a distance of 3 kilometers. The formula for work done is force multiplied by the distance over which the force is applied. So W equals F times S. The question asks for the work done by the drawbar. This means we use the force exerted by the drawbar, not the net force. That force was given as 45 kilonewtons, or 45,000 newtons. The distance, S, is 3 kilometers, which is 3,000 meters. We must always work in standard SI units, so we convert kilometers to meters. Now we substitute our values into the work formula. We have W equals 45,000 newtons multiplied by 3,000 meters. This gives us 135,000 joules. A joule is the standard unit of work or energy. This is a very large number, so it's more convenient to express it in megajoules. Since 1 megajoule is 1 million joules, we divide our answer by 1,000,000 to get 135 megajoules. Comparing this to the marking guideline, the memo also gives 135 mJ. Our answer is correct. We've reached our final question, question 3.4. This one is about the conservation of energy. The question says, an object with a mass of 50 kilograms is at rest 60 meters above ground level. It is then allowed to fall freely. We need to calculate its potential energy, its kinetic energy, and its velocity just before it hits the ground. The key principle here is the conservation of mechanical energy. For an object in free fall, the total mechanical energy, which is the sum of its potential and kinetic energy, remains constant throughout its motion. Let's first list our givens. The mass, m, is 50 kilograms. The initial height, h, is 60 meters. The initial velocity, u, is 0, since the object starts at rest. We also need the acceleration due to gravity, g, which the problem instructions tell us to take as 9.8 meters per second squared. Let's begin with part 3.41. First, let's calculate the potential energy when the object is at its highest point. The formula for gravitational potential energy, EPOE, is mgh. This formula tells us that potential energy depends on an object's mass, its height, and the strength of the gravitational field, which is g. We substitute our values. Mass is 50 kilograms, g is 9.8 meters per second squared, and the height is 60 meters. Multiplying these together gives us 29,400 joules. To make the number more manageable, we can convert it to kilojoules. Since 1 kilojoule is 1,000 joules, we divide by 1,000 to get 29.4 kilojoules. The marking guideline provides the same result. This is the total mechanical energy of the system, since the object was at rest and had no kinetic energy at this point. Now for part 3.4.2, we need to find the kinetic energy just before the object hits the ground. Remember the principle of conservation of mechanical energy? It states that the total mechanical energy at the start of the motion is equal to the total mechanical energy at the end. The total energy at the start is the potential energy we just calculated, 29.4 kilojoules, plus any initial kinetic energy. Since the object was at rest, its initial kinetic energy was 0. So, the total energy is 29.4 kilojoules. Just before the object hits the ground, we can consider its height to be 0. This means its potential energy is also 0. So, at this point, the total energy is the potential energy 0 plus the final kinetic energy. By the conservation principle, this final kinetic energy must be equal to the initial total energy, which was 29.4 kilojoules. Therefore, the kinetic energy just before it hits the ground is 29.4 kilojoules, or 29,400 joules. The marking guideline states that the change in potential energy is equal to the change in kinetic energy, which leads to the same result. The kinetic energy is 29.4 kilojoules. This answer is correct. Finally, in part 3.4.3, we need to find the velocity of the object just before it hits the ground. We know the final kinetic energy and the mass of the object. The formula for kinetic energy, EK, is 1/2 mass times velocity squared. Our goal is to find v. Let's rearrange this formula. We can multiply both sides by 2 and divide by m to get v squared equals 2 times EIK divided by m. Then to find v, we take the square root of the entire expression. Now we can substitute our values. The kinetic energy, EK, is 29,400 joules, and the mass, m, is 50 kilograms. This simplifies to the square root of 58,800 divided by phi, which is the square root of 1176. The square root of 1176 is approximately 34.293, so the velocity of the object just before it hits the ground is 34.293 meters per second. This completes the question. Let's quickly recap what we've accomplished in this tutorial. We started by stating Newton's first law of motion. Then we used kinematic equations and Newton's second law to solve for deceleration and braking force. We also calculated the acceleration and work done for a train. And finally, we applied the principle of conservation of mechanical energy to solve a free fall problem. Each of these steps involved breaking down the problem, identifying the correct formulas, performing the necessary conversions, and substituting the values carefully. I hope this step-by-step breakdown has been helpful. Keep practicing these types of problems to build your confidence and mastery. You've now completed a comprehensive review of these key dynamics concepts. Thank you for watching Math Zone African Motives. Subscribe for more tutorials to help you succeed in engineering science N4 and beyond.